In this video, I'm going to teach you how to gain a sixth sense or a spidey sixth sense of how to solve trig identity problems. And what I'm referring about when I say sixth sense is how to gain an instinct of knowing when, why, and how to substitute the different trig functions. Most professors expect you to get here, but they never actually teach it to you. It's just an expectation, and most of us fall short. So in order to gain this instinct, which I'm going to try to teach you, we first must understand these first two categories. So it's a simple three-step process. So step number one is what you should know by now. And this is SOHCAHTOA, unit circle, Pythagorean Theorem. This should be tattooed in your brain. Then step number two is knowing the trig identities. And it's quite stressful because there's like 40 of them. And I don't know about you, but I was stressed when they first showed me all these trig identities, plus more of them. But I have some good news for you. There's only 3 categories that they all come from. And one of these categories you already know is the Pythagorean Theorem. So I'm going to teach you what these 3 categories are, actually 2. And from there, you're going to be able to remember all these trig identities a lot better. Once we understand that, we're going to try to bridge the gap and go to step 3 and gain that spidey sense. So I'm going to give you a compass, something that's going to guide you along the journey, that's going to teach you how to solve these trig identity problems. Alright, so my name is Rafael Testai, and these are the 3 reasons why I'm making this video. I want to give back. I feel like a lot of students are dropping out of STEM majors, the science majors, because of math. And math is a beautiful thing that it should be explained in different ways. And this is another way that students can watch. Reason number 2 is because I get a feeling of importance when I'm able to get a really complex subject, this big block, and distill it into something small, simple, and digestible. It's almost like an eureka moment. I feel like a lot of people can't do that, and I'm very competitive in nature, and I just want to compete and be the best that I can. So that's my selfish reason for making this video. Makes me feel important. And number 3 is to review periodically. I also use these videos for myself and hopefully for others to keep my mind fresh as to what I learned in college. When an engineer graduates from college, you know all the equations, you have them all in your mind, everything's very fresh. But as time progresses, things start to fade. So I want to have a playlist, a YouTube playlist, with all these different classes that I took in college so I can watch them periodically and remember these golden nuggets. So let's get started. Step number 1 is what you should know by now. What should be tattooed in your brain by now? SOHCAHTOA, easy stuff. Then I have a golden nugget for you. This professor, Eddie Wu, which I really appreciate on YouTube, had a tip that instead of writing it out cosecant like this, CSC, write it out to cosecant, because there's a huge benefit when you do that. The 3rd letter here in purple, when you write it out, will tell you what is the reciprocal of. So if you see an S here, you know the reciprocal is going to start with S, and that's sine. Same thing again, write out secant, and you know secant is going to have a cosine in the denominator. That's what the reciprocal is for. Same for tangent. Always write them out. The unit circle. Understand and remember, that's a unit circle for a reason. The radius equals 1. And then that's how you start building. That's the connection number 1. So imagine if you had a radius of 10, this would be useless. You want the unit circle, the 1. And the benefit is that you can do SOHCAHTOA, and your denominator, so sine, or so equals sine, equals opposite over hypotenuse. And when this hypotenuse over here is 1, you're just going to keep the opposite up here. See what's happening? Therefore, you come to the conclusion, this is the big leap that you almost take, that you're going from triangles, from right triangles that can use the Pythagorean Theorem. Once you input that into the unit circle by using the beautiful 1 as denominator, you come to the conclusion that cosine is the same thing as saying the x value, and sine is the same thing as saying the y value. That's the big leap, the big take-home point that your professors want you to make. Because now you can take your triangle, once you put it into the unit circle, now you can use these principles to any angle you find, an obtuse angle, an acute angle, a right angle. You've now made this leap. And you've come, so now that you have the Pythagorean Theorem, once you replace it with cosine plus sine equals 1, you end up with this. This is what I call an anchor point. cosine squared plus sine squared equals 1. This all came from here, the Pythagorean Theorem. You already know this. So hopefully you're making this connection now, or you made the connection before watching the video. And this is going to be a huge thing to remember because, as I mentioned before, there are 3 categories, and I'm going to use blue, okay? This first category actually comes from the Pythagorean Theorem. So once you understand where this came from, you only need to understand 2 different categories, and then you're almost there. A quick thing on the unit circle, how I remember the unit circle, it's okay. I remember that it had a quadrant, and then you have 4 quadrants, but really you only need to remember 1. I just remember that. And that quadrant has 30 degrees, 45 degrees, and 60 degrees. Now I'm going to switch back to red. So it has 3 triangles. But really, I only need to remember 2 triangles because this gray triangle, so the gray, the green, the red. The gray triangle is actually the red, but just flipped. So I don't need to remember the gray one. So I've got 2 triangles I need to remember, and they come from what I call the magic triangles. So that's how you derive the information from the unit circle. If you want to pause the video, you can see. But ultimately, you get here, which is going to give you these values for the unit circle. Now, you're equipped with what you need to know at this point. If that made sense to you, we're ready to move on to the next phase. And the next phase is trig identities. Phase 2, let's talk about trig identities. So since we already discussed, I'm going to teach you the 3 categories. If we want to do tangent, TOA, is equal to opposite over adjacent. So opposite is equal to sine, adjacent is equal to cosine. Therefore, tangent is equal to sine over cosine. So that's something that we just need to know. Anytime we see tangent, it's the same thing. It needs to be tattooed in your brain, which means that cotangent, we like to write them out, is equal to 1 over tangent, which is equal to 1 over sine over cosine. We do the reciprocal, and we end up with cosine over sine equals cotangent. So anytime you see cosine over sine, anytime you see sine over cosine, you know cotangent or tangent are going to be present. Also, as I explained before, always keep an eye out for these squares. You can add the squares of sine squared plus cosine squared equals 1. If we just have these 2 here, we can substitute them by 1, so we end up with the 1 over here. It's like that spidey sense. You always need to look out for that. And really, there are not that many trigonometry functions or identities. If you just remember the Pythagorean Theorem, the a squared plus b squared equals c squared, which is the same thing as sine squared plus cosine squared equals 1, this is going to open the door for you to so many different equations and substitutions. All right, so prime example right here. Use your spidey sense to spot this over here. It has a square, which means you'll be able to substitute it over here for cosine. Anytime you can substitute 2 terms for 1 term, you're winning because you're simplifying. Now, you're not always going to do it that way, but the majority of the time, maybe 80%, you're going to want to head on this way. So it's a good instinct to have. We already went over reciprocals. Lots of notes I previously already taken. All right, so now here are the 3 different categories, which I've outlined for you. Some of my notes are in Spanish, but I'll be able to translate them for you as we go along. So category number 1, they're derived from the Pythagorean Theorem. And I'm going to teach you a trick for this later. But we have like 12 of these that they all come from sine squared plus cosine squared equals 1. And I'm going to show you how to identify all of these in the next session, in the spidey sense, sixth sense session. Then we have the sum of the angles. This is the one thing that you need to memorize and recognize. So whenever you see sine and then alpha plus beta or a plus b, you can expand that into this. And you just have to remember that. You need to be able to spot that. Cosine has a similar addition, but you flip the sign and there's a little bit of different here, but you just at least be able to spot them. Whenever you see sine and an angle and another angle, identify it and know that you can expand that. And I'm going to teach you a spidey sense technique in a moment here. So ultimately from these two, they can be plus or minus, we can derive all of these. And whenever we have tangent, remember what we said before, tangent is the same thing as sine over cosine. So then we can expand it out, and then we'll figure out as we go. And the third one is recognize that the sine to x is the same thing as saying sine x plus x. That's what we see over here. So really they all come from number 2. And there's a fourth one that I didn't mention before, but it's a really easy one. Just spot an angle, a trigonometric function, and then when it has this, remember when we used to do functions and we used to shift them? It's the same thing. So x squared and then like plus 3, when it was like y equals x squared plus 3, or f of x rather. Remember that this meant you're shifting 3 to the left, 3 units to the left. Well, same thing that's happening here. We're shifting units. And what that's saying, you can watch a lot of YouTube videos on this one, but basically the functions equal once you shift them pi over 2. So just keep an eye out for that. Now the moment that we've all been waiting for, we're going to go over the spidey sense. Third and final section in which I attempt to teach you the instincts, the spidey sixth sense, so you can solve trig identity problems. It took me several days to compose this and a lot of cognitive effort, so I hope you can appreciate it. But I think I've been able to condense something that seems rather complex into something simple that we all know. Step number 1 is when we see cosine, sine, cotangent, these trig functions, they seem like clutter because they're 3 letters. They usually contain a variable afterwards. But in reality, you could just substitute this for an arbitrary letter like A. Okay, so here I show you an example. So cosine squared, I'll just call it A squared. It just removes some of the clutter. Okay, 3 cotangent x, 3a, just arbitrary variable there. So we're looking at A, B, C's, etc. The name of the game, I'm going to show you here the main conclusion. So I'm going to start backwards. The conclusion is you're going to have expressions that you want to add, subtract, conduct some arithmetic with. And the whole premise that I've noticed from watching YouTube videos and different people, but I haven't seen anyone explain this, was that in order for you to add these fractions, so this is going to look like cosine squared x times tangent and then like a 2 here, but really these are 2 terms. This is going to be A and C. There are 2 terms that are being multiplied, and you got a denominator like sine minus 1, something like that, and that's just going to call it term B here. Okay, but I simplify it for you. We're looking at it in abstract terms, but for you to conduct this, all you got to do is have matching denominators. If you look at it, we're conducting simple arithmetic, guys. So if you want to be able to add this, here we look at step 2. One of your tools is to multiply the opposing side by the denominator here, which is like multiplying by 1, and the same thing on the left side. This is simple algebra that we all know. And really, that is what's happening here with sines and cosines. So as complex as this B may look, it may look like sine squared minus 1, something like that, equals B. So then we're going to multiply by sine squared minus 1, like this. But we're just calling this B, because it's a lot more simple to look at it in abstract terms. So once we have, here's step 2, I'm going to change the color, let's use blue. We want to have the same denominator so we can conduct arithmetic. Why do we want to do arithmetic? Because it simplifies. Because when you start adding, then you start out with 2 terms and you end up with 1 term. And this term may have a denominator at the end. So once you end up with this term, you want to get rid of the denominator. Why do you want to get rid of the denominator? Because fractions are more complicated. That's something that we learn in algebra, and I'm refreshing your mind. So to get rid of this denominator, we usually multiply by the reciprocal. And that's something that you'll see quite often here in trigonometry. If you don't multiply by the reciprocal, if you have an expression, maybe you factor something out, and then you have like something here, and then you just boom cancel out, which equals over b, something like that. So factoring it out, canceling, those are simple things that we all know, and it all clicked for me when I was able to make this transition. Just look at it as simple variables. That's all that's happening. The other thing that you need to look at is we have this trig identity, which is the expansion trig identity, and you just gotta be able to see it. As I see here, like, you gotta recognize it. Don't worry so much if you don't know what it expands to. Although it's not that hard, don't worry, just be able to identify it. Once you identify it, now, hey, I can actually expand this into this. And why do I want to expand it? Because when you expand, you're able to substitute and cancel out terms after the expansion. So it's like this sign 2a is over here. It's like a big meteorite, and the meteorite explodes, and there's like all these particles in space, or like a star exploding. And when the star explodes, you can cancel out some of these terms, or some terms you can actually assign numeric values to. And then if another term has a numeric value, then maybe these two can cancel out because they may be the same term, just a different sign in front of them. And when you can cancel them out, you'll end up with a smaller expression at the end. And we're always trying to simplify here in trig. That's the name of the game. You want to simplify. While doing this, you also want to get on what I call the Pythagorean Theorem train. So these are expressions, the only expressions that can get on this train that heads to simplicity. I like my analogies. If the Pythagorean Theorem train that heads to simplicity, but if you want to get on, choo-choo, you have to be a squared term. Why do you have to be squared? Because Pythagorean Theorem only uses squared terms. But once you get on, you can start substituting the expressions. And that's usually, you're going to have all these problems, but ultimately, they all want to get to the Pythagorean Theorem train. Choo-choo, because it heads over to simplicity. So that's what you should always keep your eye out for. Always look for these expressions that have squared. So that is the bottom line conclusion. And maybe these are the three categories for identities. I know you have that sheet of paper with like a million of them on there, but really like 90% of them, they all come from these three expressions. Category number one is the Pythagorean Theorem expression, which you can derive like 12 out of this one. And I'm going to show you a trick up there momentarily that you only need to remember this one, like magic, guys. And then all the other ones, you'll be able to derive from it very easily. This is the most important one that you simply can't just not know. You just have to be able to identify it. So here's the little I again. Just know, hey, I can actually expand that. And if you have a sheet of paper with the expansion, fine. But be able to identify it. And number three, the category number three is when you have it here in the parentheses multiplied, but you actually know it's the same thing as that. And you can derive it from category number two of the addition. So really, you got to remember just the second one. The first one you already know. The third one you can derive from the second one. So just know the second one. So I hope that simplifies. Now that you have the big picture, we're going to look at everything in abstract terms, and I'm going to give you some tools you can utilize to train to have an instinct. So in trig, we usually have two things that the professor asks us to do. Here on the left side, we just call this one. We want to show a proof of how one expression. This could be something really ugly and complicated, cosine squared minus 1 multiplied by tangent, just a whole bunch of things equal to, and then something very complicated. I'm just going to call that A equals B. All right. So that's what the professor wants you to show, a proof of how these two equal. And on the right side, they want you to solve for x. So here we're going to focus on the left side. The strategy is that you want to pick the more complex side to simplify. What do you mean by complex? Well, complex is actually arbitrary, but I'm going to tell you what I think is more complex. Here on the left side, A looks more complex because we have fractions and we got more terms. So that makes it more complicated for me. And here on the right side, we only have one term and one trig function. That seems a lot more simple. So we're going to just cut out the right side and focus on the left side and try to simplify it to get it to try to match it the right side. Why do we take this approach? Why did we pick the more complex side? Because our brains work from complexity to simplicity. That is how we work. So pick the more complex side and again try to get it to match the right side. A little bit more about what I showed before. Think of it abstractly. Sine, think of it as B, cosine as A, etc. These are just variables. We're thinking in big picture abstractly. And this allows us to conduct arithmetic. At the end of the day, that is what we're trying to do. You'll see a ton of fractions. You're really just trying to get the denominators to match. That's really the name of the game. And I'm going to show you a couple more tools to make that happen. Once you get the denominators to match, I'm just going to drill this in and repeat it. You want to end up with the same denominator so you can execute arithmetic. And once you do arithmetic, you simplify things. You get less terms, you combine. And these are basic algebraic concepts that are being executed in trig. So just because you see a whole bunch of cosine and sines and cotangents, don't let that create clutter for you. They're just A's and B's and C's. They're just variables. Always try to substitute whenever you see these are two terms, so one term, two term, into one cosine. And we'd use this by using the Pythagorean Theorem. So one term is simpler than two terms. That's the logic behind it. Sometimes you may want to keep the two terms, and usually that's for like factoring purposes, because maybe there's this term that has the 1 here and also the 1, and maybe you want to, like, I don't know, cancel them out and then turn this into a 1. But for the most part, like 80% of the time, you want to have one term instead of two. This is your spidey sense, all right? This is, if you remember watching this video, one thing, remember this thing, which is you want to always look out for whatever trig function is being squared. And that's a good thing, because then, choo-choo, it allows you to get on the Pythagorean Theorem train. And the Pythagorean Theorem train heads over to simplicity. That's the one destination. And it works because it's squared. And Pythagorean Theorem uses squared terms only. So let's say that you have, I'm going to teach you a trick that if you give me any trig function that's squared, I'll tell you what it equals. And I'm not going to need a sheet of paper with like 30 expressions or 12 of them to tell you. This is my logic behind it. So you give me cosecant squared. My name is Rafael. You're like, Rafael, what does that equal? Tell me the expression. Well, my logic is, I know that cosecant, I'm going to look at that third term, is 1 divided by sine. That's the reciprocal. So if I'm dividing by sine squared, and it's squared, it means it came from the Pythagorean Theorem. It means that we started, this is step 1, with sine squared plus cosine squared equals 1. If we divided it all by sine squared, which is what we did, I'm going to divide all the other terms. And step 3 here, this is what I end up with. 1 cotangent squared cosecant. This is the cosecant from up there. So this equals cosecant. And you can use this logic for any term that they throw at you that's squared. Ta-da! You don't need to memorize any of them. You already knew. As long as you know sine squared plus cosine squared equals 1, you're golden. Another tool that you can use, so this is almost like a toolkit. It's a little wrench here. Remember what I said about having fractions plus c, d, and wanting to get the denominators to match? When they throw a 1 at you, one of the tools you can do is convert that 1 into this the denominator over the denominator, as I have here in green. So if we look here on the right side, we converted the 1 into cosine over cosine. It's the same thing. You're subtracting 1 on both sides. These are equal. So that's the name of the game, remember? You always want to have the same denominators so you can conduct arithmetic. Wow, isn't it clicking? It's over and over again, the same thing. Yeah, once you have the same denominators, you can multiply by the reciprocal to get rid of the fraction. That's one of the strategies. Here you'll see a common factor strategy. You got AB minus B, take the b out. And once you take the b out, let me show you an example of what that looks like in the world of trig. You got a term here and another term here. They both have cotangent squared. So I'm going to take cotangent squared out and end up with this. And then we can probably get on the train because this one is squared or this one. I would look at the train now. Immediately, that's what my instinct is now. I always look at those squared and I see, all right, can we get this one on the train? And if I get it on the train, what's going to happen next? Let's look at this example now. So we have 1 minus sign here in gray. And this is actually not useful because we can't get it on the train. It's not a squared term. Therefore, what we need to do, it's we want to multiply it by 1. So anything, x, y, z, anything times 1 is always going to be itself. So this is a tool you can use, just multiply by 1, and you can use a trig expression, and the goal is so that you can get it to be a squared term, because then choo-choo, you can get it on the train. And when you get it on the train, you can simplify it. And we just took 2 terms to 1 term. We always want to make things more compact and simplify them. So there we go. Another one that you may be faced with is you look at this problem and you look at each term, okay, squared, squared. This one's not squared, okay? It means we can't substitute it. It cannot get on the train, which means we may want to convert all the other terms into signs, because ultimately we want everything to end up in sign and then some expression here, some argument, what's in the x, and that's going to help us come up with an answer that's more direct. So convert them all into one trig function. Then you need to be able to recognize this expansion identity. Not necessarily know the expansion of it, but just spot it. Have that spidey sense. Then when you see it, you know something's about to happen, so you need to expand it. And let's just do a quick recap. Why do we want to expand it? Because when you expand, you can substitute or cancel out after the expansion. And let me provide you a concrete example that I didn't give you before. So let's just focus here on the left side, okay? Don't look at the right side yet. We're going to get there. If we have this, your spidey sense should be flashing right now. Spidey, spidey. This is expansion. So expand it out. And here's a prime example. We can substitute the terms once they're expanded. They're in this face over here. We can assign them numeric values. And when we assign them numeric values, you can combine them. You can conduct arithmetic. And when you conduct arithmetic, you end up with a smaller expression. That's what the name of the game is, guys. You always want to head towards simplicity and simplify. Finally, on the right side is the other thing that the professor may ask you for, which is solve for x. So you have two expressions here, and ultimately you want to get them to one trig expression, like a sign. Whatever you may be faced with, you want to turn them into just one trig expression, and then solve for x. You also want to use the zero multiplying property. Remember when we used to do a lot of finding the zeros and quadratics? That logic comes in really handy. So if you have a times b equals 0, you know three things. Either a 0, b 0, or both a and b are 0. So you can set them up to 0 and solve for them. And lastly, when you see something like this, cosine 2x equals negative 1/2, look at the 2x as if it were just a theta. So treat it as just one angle and then solve for it. Alright, so if you enjoy this, please like, comment, subscribe. I took a lot of effort to put this all together for you guys, and I hope that you can appreciate it. Let me know what was the breakthrough moment watching this video for you. What did you learn? I'm really interested and curious into seeing how people may be responding to this. Rafael?